The sun isn't technically the center of our solar system. It's in a space called the barycenter. It depends on which planet you're standing in. The barycenter is usually closest to the object with the greater mass. So, since we're on Earth, the true center of the solar system is the sun, but not the center of it. With respect to Jupiter, the barycenter is actually outside the sun's surface. Jupiter is 318 times bigger than Earth, so the balance is different. The planets don't really revolve around the sun, but around their common center of mass. Imagine balancing a pencil on the tip of your finger. You'd have to place it right in the center so that it doesn't tip on each side. Because the pencil has its mass equally distributed, it's easy to assume that everything balances its way like that, especially in outer space. But try balancing a hammer on the tip of your toe. Chances are you'll walk out of here with a broken toe. Its true barycenter is close to the hammerhead rather than the actual center where you'd grip it. Earth and the sun's barycenter is like that hammer. The center of mass is more or less in the center of the object. Realistically, if the sun were to rotate around Earth, then our little blue planet would have to be just as big as the sun, or bigger. We can't disregard the other planets in our solar system, which means they all will have to rotate around us as well. But in the ancient days, bright minds always thought everything revolved around the Earth. They called this the geocentric model, and this made sense to them because it looked like everything above us was spinning around us. The sun and the moon played vital roles in human history, and we didn't feel insignificant in the universe until way later on. In ancient Greece and the Middle Ages, the big brains used the geocentric model to study space. It wasn't until the 16th century that that model changed. Back in those times, they couldn't even imagine that everything revolved around the sun, and they didn't have the knowledge to back any of this up. The Earth can't be the center of the solar system because it's not large enough for the job. For the conditions to suit the enormous size, life would have evolved differently. We'd probably be less dependent on oxygen. Some animals, like whales and dolphins, can stay for hours without taking a single breath. They can even sleep underwater. So the humans of the sun-sized Earth would have specialized lungs and wouldn't need to constantly be taking in air. It means that the plant life would be limited, with just a few shrubs here and there. There are trillions of trees around the world, but the main contributor to producing oxygen is the algae in the ocean. With such vast real estate of oceans and seas, the algae sitting on top are pumping out the air we breathe. Oxygen wouldn't be so abundant on this planet, but our breathing mechanisms might rely on carbon dioxide, another common gas found on other planets. If the planet is hot, then water will be scarce. We would only find it on certain parts of the planet, like mountaintops. The ground would be too scorched for anything to survive in properly. We can forget about seasons as well. The sun is currently just large enough to give us what we need. But since the Earth would be so large, and the sun would be another celestial body emanating heat, we'd always feel like we're inside a microwave. The days and nights will be different, and not much precipitation will happen. With so much heat produced in the core, earthquakes and volcanoes would likely erupt all the time. The surface would practically be a scorching plain of red magma floating around. This would be the true red planet. But if we had the same landscape like on Earth, living somewhere near the mountains could save you. The mountains would still be embedded in the core, but it would be better than staying on the ground. Some of the mountain peaks could even be 100 times taller than Mount Everest. The canyons could be so deep that the Mariana Trench would feel just like a little rupture. Animals would also behave and look different. Cold-blooded animals would have to soak up as little sun as possible so they don't burn. Animals would have to rely on migration to find water in distant lands. Birds can fly for hundreds of miles for migration season, so we'd probably see certain sleek-looking birds speeding through the air. But because gravity would be so strong on the colossal-sized Earth, the flying animals would need thinner bones and a thinner core just to take flight. The real survivors would be the microorganisms. They can live in extreme temperatures and pressures and can live without oxygen for a good while. The nights would be dark since there wouldn't be any moon to reflect the sunlight. The moon would most probably be on the opposite side of where the sun is shining, so it would forever be a floating ball in the sky. The Earth's rotational speed is the fastest at the equator, so if all the planets and the sun rotated around us, then our rotation wouldn't be so significant. New weather patterns wouldn't be good for crops. Humans would have evolved differently from what we are like now. We'd probably be shorter and stockier since gravity is so strong. And because of the soaring temperatures, we'd probably live in caves all around the world. The strongest ones would have migrated to the mountains. We'd probably have the same evolutionary path as we do now, but other physical features might be different. Our pigment would likely look different to combat the heat. The desert fox has large ears for hearing out predators and for cooling itself down in the scorching desert heat. It's possible that we would also have bigger ears than what we have now for the latter reason. We'd be a lot stronger than we are, and our bones would be thick and tough to break. Gravity is one of the key components to developing our bone density and muscle mass. This means we would unlikely need tools for hunting. This would have delayed the Bronze Age and modern civilization as we know it. With little vegetation, standing upright wouldn't be so necessary to find predators around us. We wouldn't be the fastest runners either, but we'd be strong enough to fight off a pack of strange-looking wolves. And if the Earth was supersized, then it's possible that multiple species of humans would be roaming the land in isolated areas. Some human species would grow and evolve into the intelligent thinkers of today, but some would remain the same.
They say somewhere out there, there's a pen that can work in zero gravity, at extreme temperatures, and even underwater. They say this pen can write on almost any surface, or if you turn it upside down, or when your surroundings are heated up to 570 degrees Fahrenheit. They say NASA spent millions, or probably billions of dollars, and almost a decade to develop such a pen. The problem with ballpoint pens in space is that they don't work in the conditions of weightlessness. The ink can't flow to the ball normally since gravity doesn't affect it. Instead, pressure is created in the ink reservoir and pens start leaking. Some time ago, NASA used pencils, but wooden pencils were considered to be a fire hazard in most spaceships. All because, at that time, the atmosphere inside them was 100% oxygen. The need for a super pen was obvious. But whatever the rumors claim, NASA did not create such a pen, spending a fortune on the research. Its development was sponsored by Paul C. Fisher of the Fisher Pen Company based in Chicago. He spent over $1 million and almost 10 years to make a pressurized ink cartridge. It was supposed to allow space pens to function in zero gravity and other extreme conditions. Eventually, they got a pen that could write at a temperature of minus 30 to 250 degrees Fahrenheit, which is really impressive, isn't it? The pen was patented in 1966, and 1 year later, after conducting several thorough tests, NASA started to provide Apollo astronauts with such pens. Interestingly, the rumors about NASA spending an insane amount of money on the development of space pens have been circulating for decades. They have been debunked many times, but they appear again and again. Many sci-fi movies can make you believe that everything happening in space is accompanied by some kind of a sound effect, which is a totally false misconception. In space, no one will hear you scream. You know why? There's no air in space. It's an almost perfect vacuum. And sound waves don't travel through a vacuum. They can't reach your eardrums and make them vibrate, sending signals to your brain. But it's a good thing, especially for astronauts on spacewalks. If not for the quietness of space, they would be constantly overwhelmed by the noise of solar storms. Here's another one. All comets have beautiful long tails. It's nothing but a popular misconception. In reality, comets are very difficult space bodies to spot. They usually spend large amounts of time far away from stars. There, in the darkness of space, they remain rather inactive and completely frozen. Comets only get tails once they come close to a star. That's when they start warming up. This process makes them form some kind of a cloudy atmosphere, which is called a coma, and a distinctive tail. The tail always points away from the star that influences the comet. It happens because the tail gets blown in the opposite direction by solar radiation and solar winds. That's why the tail can often be in front of the comet, not trailing after it. Now, let's look at a light year. This very notion makes us believe we speak about time here, but in reality, light years measure distance. NASA's definition of a light year goes like this: the total distance that a beam of light moving in a straight line travels in a year. And since light moves at a speed of 186,000 miles per second, a light year equals almost 6 trillion miles. Hey, do the math. Now, people often believe that in space you experience zero gravity, hence the weightlessness astronauts feel on the International Space Station. But that's not exactly true. Gravity is one of the most important forces that exist in the universe. Thanks to it, the Moon can orbit Earth, and the Sun doesn't float away from our home Milky Way galaxy. But the astronauts on the ISS experience not full-fledged, but microgravity, which means very small gravity. The gravity on the space station is only 10% weaker than the gravity on Earth's surface, but astronauts are constantly in free fall. The spacecraft, the people inside, and all the objects aboard keep falling forward, not down, but around our planet, following a specific orbit. And since they're all falling together, the crew and the stuff inside seem to be floating. That's why astronauts can move things as heavy as hundreds of pounds with their fingertips. And even though microgravity is often called zero gravity, they're very different things. Now, it may seem as if the sun is always on fire. At least that's what it looks like in pictures. But in reality, our star is a giant ball of gas. Hey, I can relate. Nuclear reactions happening in its core at all times makes the sun burn. Every second, hundreds of millions of tons of hydrogen are converted into almost as much helium. During this process, huge amounts of energy are released as gamma rays. Then these rays turn into light. In other words, the sun does emit blinding light and incredible heat. But it's not actually on fire, because no oxygen is involved in the process. A human can explode if they get into open space without a spacesuit. Well, contrary to popular belief, taking off a spacesuit during a spacewalk won't be as dramatic as it's often pictured in movies. A person will lose consciousness due to a lack of oxygen after 15 seconds of being in outer space without protection. Before it happens, the person should breathe out as much air as possible. Otherwise, this oxygen will damage their lungs from the inside. Then, without the protection of the spacesuit, which is like a mini spaceship, the pressure inside their body will drop. This will cause even more serious troubles. And even though this person definitely won't burst, they won't want to stay outside for too long. Black holes are giant, scary cosmic vacuum cleaners, they say. But in reality, black holes are more like fly traps. They don't look for things to munch on. Instead, they sit out there quite passively. Only when a star comes too close does a black hole spring into action. Even so, only those space objects that cross a certain border get ripped apart. If the sun were suddenly replaced with a black hole, Earth's orbit wouldn't change. At the same time, Earth's temperature would be different. There would be no solar wind, and no magnetic storms created by the sun would affect our planet. And let's say the black hole that replaced the sun had the same mass as our star. Then, according to the law of physics, Earth would have to come very close to get pulled into this black hole.
Venus has exceptionally high temperatures, hot enough to melt lead. It's the hottest planet in our solar system, with a high-pressure environment and super strong winds. The winds there are 50 times faster than the planet's rotation. It's getting stronger over time, and scientists don't know why. But they did find something interesting in the planet's clouds, a potential sign of decaying biological matter. Could there be life then? Not quite, since Venus has a dry, windy atmosphere and doesn't have enough water for life to develop. Rings around other planets are more common than we thought. Saturn's rings are the most famous and spectacular ones. They partially consist of reflective, sparkly water ice, and you can't see anything like that in the rest of our solar system. Jupiter, Uranus, and Neptune have ring systems too, and those most likely consist of dust and rocky particles. And not just planets. Astronomers found out rings were around one asteroid as well. Speaking of rings, why do you think that Earth doesn't have them? Gas giants have rings, while the rocky ones don't. Two theories explain how rings form. They could be the remains from the times when planets were forming. Or they could be leftover material of an impact that destroyed an unknown moon, or gravity broke apart this moon of its parent planet. It's not clear why only the gas planets have rings. They formed in the outer area of our solar system, while rocky planets only in its inner circles. May be a good clue. Maybe these inner rocky planets had just better protection from strong impacts that could have formed rings. Also, there are more moons in the outer solar system. And there are more rings there. Another thing may be that bigger planets have a bigger volume, so a ring system can remain stable there. Some theories even say that Earth used to have a ring system. A long time ago, our planet collided with a Mars-sized object, which most likely resulted in a dense ring of particles and debris. But our story was a bit different than the outer planets, and those rings probably combined and formed the Moon. Do we know the shape of the universe? Einstein had a theory of general relativity. It said that the universe could be in one of these three forms: closed like a sphere, open like a saddle, or flat like a piece of paper. Its shape determines whether it's infinite or not, and whether it will expand forever or maybe collapse at some point. The shape of the universe depends on its density and rate of expansion. One of the best ways to determine its shape is to use something called the cosmic microwave background. It's the relic afterglow, something that's left of the Big Bang. Sound waves that were moving through the universe in its early stages produced quite small spatial variations in the temperature of its faint light. The result of these studies showed that the universe probably expands in all directions, which means it's flat. How come our sun is hot while the moon is cold? The sun gives off heat because its core is extremely hot. In there, the pressure is pretty high. The hydrogen turns into helium. That's how the sun creates light and heat. The solar light and heat are enough to light up our days on Earth, as well as support life here, even though the sun is around 93 million miles away from us. The moon is not hot because it doesn't have an atmosphere, so it can't absorb sunlight as our planet does. Its surface gets very hot in the daytime, about 210 degrees Fahrenheit, but since there's no atmosphere, the temperature drops extremely during the night to negative 279 degrees Fahrenheit. The sun is hot, no doubt there, but the space around it is very cold. Heat is the energy objects store inside of it. Temperature is how we measure if something is hot or cold. So when you transfer heat to certain objects, its temperature goes up. Take it away, and the temperature goes down. You can transfer heat in three different ways: convection, conduction, and radiation. Convection works within gases and liquids, and conduction is for solids. The temperature only affects matter. Space doesn't have enough particles. It's nearly a complete vacuum, which means transferring heat is not effective. The only way to do it is through radiation. When the heat coming from the sun falls on an object in the form of radiation, the atoms that make up that object will absorb energy. This energy moves the atoms and makes them produce heat throughout this process. In space, temperatures of the objects stay the same for a long time. Cold objects stay cold, and hot ones stay hot. If you place anything outside of the Earth's atmosphere and expose it to direct sunlight, the sun will heat it to about 250 degrees Fahrenheit. Objects in outer space that surround our planet and don't receive sunlight directly are at 50 degrees Fahrenheit. The temperature is like this because there are molecules that escape our atmosphere, so the sun heats them. We used to think that water was really rare in space, but now we know there's water ice across our entire solar system. For starters, you can usually find water on asteroids and comets. It's also in craters on Mercury and the Moon that are in permanent shadows. On Mars, you'd find ice at its poles, under the surface dust and in frost. It might not be enough to support human colonies up there, but it's still something. Some other bodies in our solar system also contain ice, like the dwarf planet Ceres and one of Saturn's moons. Europa, one of Jupiter's moons, could be one of the most likely candidates we know about that could contain life. it probably has an entire ocean under its frozen and cracked surface. It could have twice as much water as all oceans on our planet together. Titan, the biggest of Saturn's moons, also has a liquid cycle, but it's not water. Its cycle moves materials between the surface and the atmosphere. At first, it sounds like the water cycle we have on Earth. But immense lakes on Titan are filled with ethane and methane. There's a chance they're over a layer of water. Neptune is about 30 times as far from the Sun as we are. Of course, it gets significantly less light and heat than Earth, but it also radiates way more heat than it's generating. There are more things happening in its atmosphere, especially if you compare it to its neighbor, Uranus. Uranus is closer to the Sun, but it still radiates the same amount of heat as Neptune. The winds on Neptune are insanely strong, 1,500 miles per hour. No one still knows why. It could be a gravitational contraction, energy coming from its core, or the Sun. I hope we'll eventually find out.
That's it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends. Or if you want more, just click on these videos and stay on the bright side.